On July 11th, 2022, at approximately 5 p.m. Eastern Time, a group of astronomers of the Space Telescope Science Institute in Baltimore, Maryland, opened the first batch of calibration data from the James Webb Space Telescope. And for approximately 90 seconds, nobody in the room spoke. The monitors displayed a region of sky no larger than a grain of sand held at arm's length, and inside that grain were thousands of galaxies. Stretching back 13 billion years into the past, the problem was that some of those galaxies should not exist. That silence was not awe, it was confusion. It was the sound of a theoretical framework trusted for decades, encountering data it could not accommodate. Within weeks, preprint servers were flooded with papers carrying titles that ranged from cautiously alarmed to openly panicked. A new population of massive galaxies at high redshift. Impossibly early galaxy formation. The crisis at cosmic dawn. The language of science, usually measured and conservative, had acquired a tremor. What JWST found in those first deep field images was not a minor anomaly requiring a small adjustment to existing models. It was a fundamental challenge to the story we have told ourselves about the origin and evolution of the universe for the past 60 years. This is that story, and this is how it may be falling apart. The standard model of cosmology is called Lambda-CDM. Lambda refers to the cosmological constant, a term representing dark energy, the mysterious force driving the accelerated expansion of the universe. CDM stands for cold dark matter, the invisible substance that provides the gravitational scaffolding for galaxy formation. Together, these two components account for approximately 95% of the total energy content of the cosmos. The remaining 5% is ordinary matter. Atoms, molecules, stars, planets, people. Lambda-CDM is built on the foundation of the Big Bang Theory, which posits that the universe began 13.8 billion years ago in an extraordinarily hot, dense state and has been expanding and cooling ever since. This framework is supported by three pillars of evidence. The first pillar is the expansion of the universe, discovered by Edwin Hubble in 1929. Distant galaxies are moving away from us, and the farther they are, the faster they recede. Run the clock backward, and everything converges to a single point. The second pillar is the cosmic microwave background radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. This faint thermal glow, uniform in every direction, is the cooled remnant of the primordial fireball. Its temperature, 2.725 Kelvin, and its tiny fluctuations match the predictions of Big Bang nucleosynthesis with extraordinary precision. The third pillar is the abundance of light elements. The Big Bang model predicts specific ratios of hydrogen, helium, deuterium, and lithium produced in the first few minutes after the initial expansion. Observations confirm these ratios to within a few percent. These three pillars have made the Big Bang the most successful cosmological model in history. For decades, it has been treated not as a hypothesis, but as established fact. Textbooks present it without caveat. Careers have been built on its assumptions. Billions of dollars in telescope time have been allocated based on its predictions. And then Webb opened its eyes. The problem is galaxies. Specifically, galaxies that are too massive, too structured, and too mature for the epoch in which they appear. Galaxy formation in Lambda-CDM follows a hierarchical model. Small structures form first. Tiny fluctuations in the primordial density field, imprinted during the inflationary epoch, grow under gravity over hundreds of millions of years. These fluctuations collapse into dark matter halos, which attract gas, which cools and condenses into the first stars. stars cluster into protogalaxies. Protogalaxies merge into larger galaxies. The process is slow, incremental, and cumulative. According to this model, the first galaxies should be small, irregular, and chaotic, dwarf galaxies. Clumps of young, blue stars surrounded by turbulent gas. Structure should emerge gradually over billions of years of mergers and accretion. Spiral arms, central bulges, quiescent stellar populations. All of these are features of maturity. They should not appear in the first 500 million years. JWST found them in the first 300 million years. The galaxy designated ZF, UDS 7329 is the most dramatic example, but is far from the only one. This galaxy exists at a redshift of approximately 3.2, which places it roughly 11.8 billion years in the past. Spectroscopic analysis by a team led by Thamian Aniakara at Swinburne University of Technology revealed that ZF, UDS 7329 is not merely old. It is dead. Its star formation ceased approximately 1.5 billion years before the light we observe was emitted. This means the galaxy formed the bulk of its stellar mass within the first billion years after the Big Bang, assembled itself into a coherent, massive structure, and then stopped forming stars entirely. The mass of ZF UDS 7329 is estimated at approximately 200 billion solar masses. To put this in context, the Milky Way, a large spiral galaxy that has been evolving for 13.6 billion years, contains approximately 1.5 trillion solar masses, including its dark matter halo. ZF UDS 7329 achieved a significant fraction of this mass in 1/10 of the time. This is not supposed to happen. The physics does not allow it. Galaxy mass is determined through spectral energy distribution fitting. Astronomers measure the light emitted by a galaxy across multiple wavelengths, from ultraviolet through infrared. They then compare this observed spectrum to a library of model spectra generated by stellar population synthesis codes. These models account for the ages, metallicities, and masses of the stellar populations that produce the observed light. By finding the best match, astronomers infer the total stellar mass. JWST's advantage over previous telescopes is its infrared sensitivity. The near-infrared camera, an IR cam, and the mid-infrared instrument, MIRI, observe at wavelengths between 0.6 and 28 microns. At high redshifts, the ultraviolet and optical light emitted by galaxies is shifted into the infrared by the expansion of space. Hubble could barely detect these objects. Webb sees them clearly, and what Webb sees is impossible under current theory. Between 2022 and 2024, multiple independent teams identified galaxies at redshifts exceeding 10, corresponding to the first 400 million years after the Big Bang, with stellar masses between 1 billion and 100 billion solar masses. These objects are not protogalactic fragments. They are fully assembled galaxies with established stellar populations, some showing evidence of chemical enrichment that requires multiple generations of star formation and supernovae. The hierarchical model cannot produce these objects in the available time. Even if you maximize every parameter, assume the most efficient star formation rates, minimize feedback from supernovae and active galactic nuclei, and allow dark matter halos to collapse at the theoretical maximum rate, the numbers do not work. You cannot build a 10-billion solar mass galaxy in 300 million years through mergers and accretion. The universe was not old enough. The dark matter halos were not massive enough. The gas had not had time to cool and fragment efficiently. Some theorists have proposed solutions within the existing framework. Perhaps star formation efficiency in the early universe was dramatically higher than in the local universe. Perhaps primordial black holes, formed in the first moments after the Big Bang, serve as seeds for rapid galaxy assembly. Perhaps feedback mechanisms were weaker, allowing gas to cool and collapse more efficiently. Each of these proposals requires significant modifications to Lambda-CDM, not adjustments, modifications, new physics, new parameters, new variables added to a model that was already carrying two enormous unknowns: dark matter and dark energy. This brings us to the second crisis. The Hubble tension is a discrepancy between two independent measurements of the expansion rate of the universe. The cosmic microwave background, as measured by the Planck satellite, implies a Hubble constant of 67.4 kilometers per second per megaparsec. Local measurements, using Cepheid variable stars and type I supernovae as distance markers, consistently yield values near 73.0 kilometers per second per megaparsec. JWST was expected to resolve this tension by improving the calibration of Cepheid measurements. In 2023, a team led by Adam Rees used Webb data to re-examine Cepheid variables in Type I supernova host galaxies. The result: the local measurement held. Webb confirmed 73, not 67. The tension is real and statistically significant at more than 5 sigma, the threshold for a discovery in physics. A 5 sigma discrepancy means the probability of this difference occurring by chance is less than 1 in 3.5 million. This is not a measurement error. This is a signal. Something is wrong with the model. If the expansion rate is truly 73, then the universe is younger than Planck data suggests, or the physics governing expansion has changed over time, or there's a systematic error in our understanding of the early universe that propagates through every calculation based on the CMB. Now step back and look at the full picture. We have a model that requires 95% of the universe to consist of substances we have never directly detected. Dark matter has been searched for in underground laboratories, particle accelerators, and space-based detectors for over 40 years. No confirmed detection. Dark energy is even more elusive, a property of space-time itself that we can describe mathematically but cannot explain physically. These are not predictions of a complete theory. They are placeholders, variables inserted into equations to make them fit observations. In the 2nd century, Claudius Ptolemy constructed a model of the solar system in which Earth sat at the center and the planets moved in perfect circles. When observations did not match, he added epicycles, smaller circles upon circles, adjustable parameters that could accommodate any discrepancy. The Ptolemaic model was not wrong in the sense that it could not predict planetary positions. It predicted them brilliantly. It was wrong in the sense that its foundational assumption, that Earth was the center, was incorrect. The epicycles were mathematical patches applied to a structural error. Dark matter and dark energy may be the epicycles of modern cosmology. Not because they are necessarily fictitious, but because they may be symptoms of a deeper misunderstanding. We observe gravitational effects that do not match the visible mass. So we invent dark matter. We observe accelerated expansion. So we invoke dark energy. We discover galaxies that form too quickly. So we adjust star formation efficiency. We measure an expansion rate that contradicts the CMB, so we propose early dark energy or new neutrino species. Each addition saves the model temporarily, but the model grows heavier with each rescue, and at some point, the weight becomes unsustainable. Alternative frameworks exist, though none has achieved the predictive success of Lambda-CDM. Conformal cyclic cosmology, proposed by Roger Penrose, suggests that the Big Bang was not the beginning of time, but a transition point between eons. In this model, the heat death of a previous universe, where all matter has decayed and only photons remain, is mathematically identical to the conditions of a new Big Bang. The universe cycles through infinite iterations. This framework could accommodate massive early galaxies if structure from a previous eon carried over into the current one. Penrose has claimed to find evidence for this in anomalous patterns in the cosmic microwave background, but these claims remain highly controversial. The tired light hypothesis, proposed in the 1920s as an alternative to cosmic expansion, suggests that photons lose energy as they travel through space, causing the observed redshift without requiring an expanding universe. This idea was largely abandoned because it could not explain the time dilation observed in type I supernovae at high redshifts or the surface brightness characteristics of distant galaxies. However, modified versions have resurfaced in the wake of the JWST crisis, though. They remain firmly outside the mainstream. Modified Newtonian dynamics, or MOND, attempt to explain galactic rotation curves without dark matter by altering the law of gravity at very low accelerations. It has had some success at galactic scales, but struggles with galaxy clusters and has no relativistic formulation that can replace general relativity at cosmological scales. None of these alternatives is ready to replace Lambda-CDM. But the fact that they are being discussed seriously in journals that would have dismissed them 5 years ago tells you something about the state of the field. The foundation is cracking. What happens when the foundation of a scientific paradigm cracks? History provides examples. The transition from Ptolemaic to Copernican cosmology took over a century and was resisted at every stage. The transition from Newtonian gravity to general relativity was faster, but required the specific genius of Einstein and the coincidence of a solar eclipse that could test his predictions. The quantum revolution upended classical determinism and required an entirely new mathematical language. Each transition was painful. Each involved a period where the old model was clearly failing, but no complete replacement existed. Physicists call this a crisis period. We may be entering one now. The JWST data does not disprove the Big Bang in the sense that it invalidates the expansion of the universe or the existence of the cosmic microwave background. These observations remain robust. What the data challenges is the specific narrative we have built around the Big Bang. The timeline, the growth rate, the hierarchical assembly of structure, the smooth, predictable evolution from hot plasma to the cosmos we observe today. The universe is older than we thought, or more complex, or governed by physics we do not yet understand. The galaxies that should not exist are staring back at us from the edge of time, massive and silent, demanding an explanation we cannot yet provide. And perhaps that is the most unsettling realization of all. We have spent a century constructing a story about where we came from. We told it with confidence. We taught it in classrooms. We built telescopes specifically designed to confirm its final chapters. Instead, those telescopes handed us a different book, one written in a language we are only beginning to recognize, one whose first pages describe a universe far stranger, far older in its complexity, and far less cooperative with human theory than we ever imagined. The 13 billion year story of the cosmos may not be wrong, but it is almost certainly incomplete, and the parts we're missing may be the parts that matter most. We are not at the end of cosmology. We are at the end of the beginning, And what comes next will require us to do the hardest thing science ever asks of its practitioners: to admit that we were wrong and to start again.